So yeah, good afternoon again, and welcome to the CSP seminar, Communication Signal Processing Seminar. Yes, I should first start by thanking our thanking Shelley Falcam for arranging this. I do want to thank her every time because it's not enough. And I also want to thank the sponsors, KLA and the two research groups, NCIS and SIPML. So today we have Ali Al-Gamal, who's an assistant professor in the ECE department at Purdue, who's a speaker. So Ali is an assistant professor, as I mentioned, and he received his PhD degree in ECE and a master's degree in mathematics from the University of Illinois at Urbana-Champaign, the PhD in 2014 and the Master of Science in Mathematics in 2013, respectively. Prior to that, he received the his master's in electrical engineering from Nile University and a BS degree in computer engineering from Cairo University. These were in 2009 and 2007, respectively. His research interests include information theory and machine learning, and as you would see from the abstract in today's talk, he's going to try to cover both aspects today. Ali has received a number of awards, including the Purdue Seed for Success Award, the Purdue CNSIP Area Seminal Paper Award, the Purdue Engineering Outstanding Teaching Award, the DARPA Spectrum Collaboration Challenge SC2 Contract Award, and Preliminary Events 1 and 2 Team Awards, and the Huawei Innovation Research Program HIRP Open Award. He's currently serving as an associate editor in the area of machine learning and AI for wireless, the IEEE Transactions and Wireless Communications, and as a reviewer for the American Mathematical Society Math Reviews. So Ali, I'll give you the floor, and please.
Thanks a lot, Vijay, and thanks for inviting me to give this talk. And I made the request to visit Michigan, and I'm happy to have the opportunity, even if virtually. Ideally, I would have loved to visit your campus, but that will do right now. And I'm happy that I met with the students this morning, and I'll have a couple more meetings tomorrow. So basically, this talk is about the activity, research activity in the lab I am managing at Purdue. And the idea is to stir collaboration. So I'll try to shed light on the different problems and why we think these problems are good that we are considering, and hopefully that becomes a start of something that's good. So the name of the lab is Family, and it stands for Foundations and Applications of Machine Intelligence, Lab for Society. And my favorite part is the last word, which basically means that we're trying to do useful things, not just science. So most of the work is on deep learning. And just to give you like a broad idea, if you have never, and I'm sure you have, like of what's happening. So basically, it's a machine learning approach that's got traction in the past decade because of its ability to process large data sets through basically function fitting. So a series of linear transformations that are followed by nonlinear activations, and with defining the right error function or the right cost function, and with very simple optimization strategies like gradient-based learning that depend only on first-order derivative information. It seems to succeed in many applications. It has a very particular philosophy about using a large parameter space to optimize or to find good functions for these very large data sets. So it's because of its success, it's becoming kind of a de facto, and maybe in the next decade, it's expected to go into computer architecture. And this is kind of a paradigm change, because once it goes into computer architecture, it will define what is computationally efficient and what is not, right? So that will even make it or justify its use in different applications, even if you know a traditional way of carrying out the task, because it can become more computationally efficient to use deep learning as the architectures that are widespread becomes like more efficient at doing, or more steered towards doing deep learning algorithms. So in general, it's suitable with inaccurate mathematical models and large data sets. Now, two important aspects of deep learning that I'll always keep coming back to them, and try to keep mind of them while doing research in any application or even in the foundations, is one is feature selection, which is related to the interpretability of the deep learning algorithms. Like when you have a machine learning task and you carry it out successfully, then what features of the inputs did you rely on, and what features were extracted in the hidden layers. The other aspect is a security aspect, which is basically like crucial to the success of these algorithms and whether they will be applied in practice or no. It's basically the robustness of these deep learning algorithms to what's called adversarial attacks, which is basically perturbations of the input data. So I'll discuss 5 problems. Most of the time will be in the first one, which is an information theoretic framework for machine learning that was introduced in 1999 and 2000. And it's starting to get a lot of attention. So we'll basically try to discuss high level what this framework, which is called the information bottleneck, is about, and how is it how does it intersect with deep learning or designing deep learning algorithms, as well as explaining how they work or providing a theoretical benchmark for deep learning algorithms. And then I'll talk a little bit about each of the other 4 problems. The second one is adversarial deep learning. It's the security problem related to deep learning algorithms. And then I'll talk about 3 applications. One is applying deep learning for wireless, why we think this is a good idea and what we have done so far. And there I will highlight our participation, Purdue's participation in the DARPA Spectrum Collaboration Challenge. And then I'll talk about the application of machine learning for network security and specifically network intrusion detection. And I'll highlight a patent that we are actually filing the non-provisional for, or the final application for this or next week. And lastly, I'll talk about the application of machine learning, not just the application of machine learning, but the problem in general of autonomous racing, building racing cars that drive autonomously. And I'll highlight our participation in the Indy Autonomous Challenge, which is taking place right now and will conclude next year. So the information bottleneck. So the formulation of the information bottleneck is a very simple formulation. Okay, and these slides will have some math into it, but don't worry too much about it. So you can read the slides on your own, but I'll try to highlight the main ideas. So the information bottleneck formulation says the following. Let's say I have a random variable of observations, X, and I have another random variable representing the learning task, or what's called the relevant data features, Y. So Y is my task, X is my observations. And I want to choose a representation, Z, such that this representation is compressed as much as possible. But the definition of compression in the information bottleneck is a little bit unusual, because traditionally, compression would mean that I am basically, let's say, minimizing the entropy of Z, right? Minimizing the cardinality of Z or so on. Here, the definition of compression is basically minimizing the amount of information that Z carries about X, about the observations, right? So we want to know the minimum amount of information that we can have about the observations such that we are satisfying a constraint about the amount of information that is relevant to the learning task, right? So you are minimizing the mutual information between X and Z such that the mutual information between Y and Z is bigger than a certain threshold, okay? Now, few things before I address the bullets that are pointed out above. One of them is the definition of compression. It's a little bit unusual, and I highly encourage you to read the paper like for the philosophy behind that definition instead of minimizing the entropy of Z, let's say. The other one is that basically that's the difference between it clarifies or it captures the difference between a pure optimization problem. So you're not just minimizing the amount of information you carry out about the observations. You have an objective, and that objective is to reach a good enough solution, right? So it's not that I want to maximize IYZ without bound. The learning task defines a threshold in the information bottleneck framework, right? So I have what's called a good enough solution. And actually in the deep learning book, without even discussing the information bottleneck, and that was not the subject at all, they always come back to this deep learning book. I mean, the one that's co-authored by Ian Goodfellow and Joshua Bengio. They always come back to this concept of a good enough solution, that in learning, you want a solution that just works. And one reason is that because typically you have access only to the training data. So even keeping optimizing the fine details might not be a good strategy anyway, because that might hurt generalization. It might make you overfit, right? So there is always this practical philosophy that goes into every like all the details of the optimization algorithms for training deep neural networks, as well as regularization strategies, that our goal is just to get a good enough solution, right? Not to keep maximizing the mutual information between the representation and the relevant data features, right? So this is, I think, some of the reasons why this is becoming suitable for machine learning, this formulation. Now, so this formulation can be thought of in general as representation learning. You want to learn a representation with that satisfies certain constraints. Now, a little bit like about the high-level view of this this formulation. So this formulation is very similar to rate distortion theory in information theory, right? Which is, you have a source X, you want to compress that source such that you are satisfying a distortion function. Okay. Now, I will try to present a little bit of a different view of that formulation, which is basically, when information theory came out, it came out in 1948. It came out basically for communication, right? It was not, the main objective was a mathematical theory for communication. That was the name of the paper. One of the ideas that Claude Shannon highlighted, or like one of the ideas that were milestones in his line of thought, was basically to get rid of the semantics, right? So in the communication problem, that we want to communicate bits and we don't care about the context of these bits, okay? Now that made progress at that time, right? But now, and this is by no means a concrete thought that I have, but I think it's relevant, that this information bottleneck formulation is very relevant to bringing semantics into the communication problem. And in that case, the communication problem would look very similar to the machine learning problem. What I mean by bringing semantics back is basically, when I communicate audio, is different from communicating video. There is common information between the transmitter and the receiver about the context, right? So it's communication, right, which is minimizing information about the source because of the channel capacity constraints, right? But with respect to capturing certain information that's important, okay? So just keep it in mind, and we can discuss it offline if you're curious about this second bullet up there. Now let's go back to the information bottleneck formulation. One of the advantages of this formulation is that if you write the Lagrangian formulation for it, right, then it becomes very feasible to solve if X, Y, and Z are discrete, right? And this is no surprise, because we know that in rate distortion theory, okay? So the Lagrangian formulation is basically minimizing the mutual information minus a Lagrangian multiplier times what you're capturing about the relevant data tasks, subject to a Markov chain assumption that basically your representation depends on the relevant data features only through your observations, right? So there is no other way to get side information about the relevant data features other than the observations, okay? Now, other than like the fact that this formulation admits a solution for the discrete case, This formulation actually has an interpretation, in a nice interpretation that we can think of in terms of the machine learning problem, which is basically that this IXZ is an intrinsic regularization factor, right? So ideally, I'm trying to maximize the goal of machine learning is to fit, right? So I'm trying to maximize the mutual information between the representation and the relevant data features as much as possible, right? Now, what's holding you off from doing that to the extreme is basically the other term. And in machine learning, that other term is usually a regularization term, right? So here our regularization term is basically the mutual information between the representation and the the observations. Okay, so I think this is also another item that's not very concrete to anybody, I think, in the like from reading the literature, and definitely not to me, but it's very useful to keep in mind that this is actually a very accurate analogy, that this IXZ can be thought of as a regularization term. Okay, now in rate distortion theory, in the discrete case, there is something called self-consistent equations, and this is the key behind finding a solution, that there is a solution in the discrete case. The same thing happened in the information bottleneck, right? So this is basically like an image from the one of the original papers, but I want to take one line and focus on it here, is that it says the Lagrange multiplier, right, beta, has the natural interpretation of inverse temperature. Right? What does temperature mean? Temperature means, if you draw an analogy between the optimization problem that you have, or that we have, and annealing, right? So annealing is something that happens in thermodynamics, and basically it means that if the temperature is high, then I am moving, like I'm doing very wild moves across the parameter space to explore it as fast as possible, and then as the temperature goes down, right, then I'm fine-tuning my optimization. Then I'm basically in a good neighborhood of the parameter space, and I'm doing fine-tuning to find a good solution. Okay. Now, beta inverse has the interpretation of a temperature, because in the analysis of the Lagrangian formulation of the information bottleneck, we can reach that conclusion. And here x tilde is z, and I'm sorry about the change in notation. Basically, this is saying what? This is saying that so this is partial derivative notation. The sensitivity in the amount of information that you carry about the relevant data features with respect to the amount of information that you have about the observations, that sensitivity is very high for small values of beta, and kind of saturates as beta grows, right? So let's think of that, let's have like a further analysis of this. Let's say I start with beta equals 0, right? Beta equals 0 means I don't have any learning constraint. So basically this x tilde, or so I'm minimizing, right? So this z or x tilde, right? If beta is 0, I make it deterministic, because I don't want to learn anything. I minimize IXZ to the extreme, so I make it 0 by making z deterministic. As I increase beta, the learning task kicks in, right? Small values of beta mean what? Means that I am required only to carry very little information about the relevant data features. Large beta, I'm required to carry a lot of information about the relevant data features, right? So this is saying what? That in the small beta regime, you are very sensitive to any change, to like if you capture a little bit more information about the observations, that can give you a huge gain, right? So in the discrete case, one crude way of thinking about capturing more information about the observations is basically increasing the cardinality of z, right? So instead of z having an alphabet of 2, my representation, I make it having an alphabet of 3, right? Think of it in a neural network. Instead of the hidden layer having 2 units, I increase by 1 more unit. So I increase the expressive power of the network. And this is a term that people in deep learning literature use a lot, the expressive power or the complexity of the network. And it doesn't have a concrete definition. But here, you can think of it of the information bottleneck as providing a guideline for that expressive power idea, right? Because it tells you in the current regime that you are at, how much gain can you get in terms of learning performance from increasing the complexity of your network, or increasing the capacity of your network, of your neural network, right? So, and then the story actually becomes more interesting than this. It's not only that this beta has an analogy of inverse temperature, and that makes it that can enable getting guideline about how much capacity of a model that you need to achieve your learning objective. But there is something very interesting that happens in this when we try to solve this information bottleneck formulation. And just to give you an idea, the IB curve, what's called the IB curve, is basically a plotting of IXZ versus IYZ for different values of beta. Okay. Now, something called phase transitions happen, which is basically a second order, right? In terms of second order derivative, second order change that happens to the IXZ and the IYZ curves at certain values of beta. Right? So basically the curves would look like this, right? So second order meaning curvature, right? So if something convex all the way, right? Or something quadratic all the way, right? So it's perfectly like it looks ideally convex, you can think of it this way, then the second order is fixed. When the second order changes, then you have these transitions here, right? Now, one other way to think of the phase transitions is that something called bifurcation happens, right? If you basically plot, let's say I plot the curve corresponding to a certain, I am in the discrete case, and I plot the curve, the IB curve, corresponding to Z with alphabet equal 2, right? So that's corresponding to 2 clusters of the data. And I plot with it the curve corresponding to 3 clusters, right? When beta is very small, 2 clusters or 3 clusters will have a similar performance, right? So a similar IB curve. Why? Because the 2 is enough, right? Beta is very small, means the learning task is very easy, right? So 2 is enough. So they are coinciding. And then at a certain beta, they bifurcate, meaning that you start achieving learning performance with the model that can represent 3 clusters that is different, significantly different from the learning performance from the model that can only represent 2 clusters, right? So that tells you that even if you have a regression problem or any classification problem, right, the right number of classes might not be the number of classes suggested by the application. The right number of classes is suggested by the distribution of the observations and the learning task, right? And for every pair of learning task and observations, you have a right number of classes that you should learn in the hidden layers of your network or in the intermediate steps of any machine learning algorithm in general, right? So that's one of the nice insights that you can get from information bottleneck. Now, other insights are technical, which is basically in order to find the IB curve in general, not just for the discrete case, finding the phase transitions can facilitate that process, right? Because it can give you hints, even though you cannot characterize the full IB curve, you know which region to search for, right? And there are many algorithms that are related to things that exist in statistical optimization in general, like something called maximum correlation. And I wouldn't get into the details of that. But this is basically the very problem we are considering right now, is how to come up with a computationally efficient way of finding phase transitions in the general case, okay? Now, let's go back to the utility of this, right? So other than giving a guideline to the expressive power or the capacity of the learning model, right? People have been inspired by information bottleneck to come up with regularization strategies, right? One of the strategies is what's called confidence penalty, and that was introduced, I think, 2017. And here, just to simplify the math, the first term, so J is the cost function, right? The first term in the sum, this is summation over the examples, or think of it some examples in a mini batch in a deep learning algorithm. And the first term is just the cross entropy cost, which is the typical cost used for classification in TensorFlow or PyTorch libraries, okay? And then that second term is an entropy term, right? So that second term is saying what? It's saying that I'm not trying to fit exactly to the training data, but I'm artificially injecting uncertainty. Y represents the labels, right? Here in that notation, X is the input vector, okay? So I am increasing the entropy intentionally, or putting pressure on the network through this regularization term to increase the entropy of obtaining the label given the observations, right? So even though, let's say, a certain image, I always say it, I always, let's say I'm trying to classify whether an image has a face of a human or no. And a certain image, I saw it in the training data, it has the face of a human, right? Then that term puts pressure on the network to basically distort the training labels, right? And this is similar to something called label smoothing in deep learning, which is in the classification case, similar to flipping coins intentionally, right? So I flip the label, right? The classification label that I see in the training data intentionally. Here, instead of this flipping process, we use the entropy as a guideline, right? The Shannon entropy. And that seems to get some success in practice, but it's an interesting strategy, and its analysis could be similar to the analysis of the information bottleneck, because in the information bottleneck you have this IXZ. You can think of it as a regularization term. Okay. Now another method that's inspired by the information bottleneck, what's called the deep variational information bottleneck, and basically it's the idea is simple. Just forget like the math here. It's that this IZY and IXZ that we are trying to find, they bound them, right? So they bound one from below and one from above to be consistent with the direction of the optimization problem, right? And then, so you only have access to empirical data, right? So some of these terms, you can only obtain them in a variational estimation way, right? And to do the variational estimation, they use tools that are available in like deep neural networks, like the variational autoencoders, for example, to do the variational estimation. Now, I'll not go into the details, but to summarize, it finds a bound on the information bottleneck through a deep learning simulation, okay? Now, it turns out, and surprisingly, at least the authors say that they didn't intend that in the first place, that this deep VIB achieves good results against adversarial attacks, right? And that brings me to the second topic, which is basically adversarial deep learning attacks. The idea here is very simple. Is basically, let's say you have images. People found out that because these deep neural networks rely on their training only on first order derivative information, which is gradient based learning, that you can perturb the data, add small perturbations to the data, such that you move in a direction that's perpendicular to the decision boundary. So imagine a classification and you have a decision boundary like this, and you have a point here, then you move in a direction perpendicular to the decision boundary. And one of the simplest attacks that explain the idea is what's called fast gradient sign. So let's say I take the gradient of the cost J with respect to the input X, right? And theta is the parameters of the model, X is the input, Y is the training label. So I compute the cost, I compute the gradient of the cost with respect to the input, and I move in the direction of the sign of the gradient, right? So one could think of this high level as moving in a direction perpendicular to the decision boundary, right? Then basically with very simple, very small perturbations that are even not visible or hardly visible to a human eye, then it fools the deep neural network, right? So it's a little bit not very surprising that deep VIB is a good defense, because deep VIB actually hits a point in the trade-off between the training error and the robustness, right? So think of it this way. If you custom tailor the network exactly to fit the training data, you're probably vulnerable to any small change. But as you go away from fitting exactly to the training data by injecting uncertainty, which is the philosophy of the information bottleneck, right? Injecting uncertainty in a principled way according to the entropy metric, then basically this adds robustness because the decision boundaries are not custom fit to the training data, all right? So when you do something like moving in the sign of the gradient, you're not necessarily moving perpendicular to the decision boundary. Now, one thing I want to highlight and related to the third topic that I will discuss is that this topic is very relevant to wireless, in the wireless scenario, right? Because this problem came about in a little bit of an unnatural setting, because people said, okay, like if I use deep learning in self-driving cars, then maybe I can dust traffic signs, physically change traffic signs to fool the self-driving car. Now that's a much more difficult process than perturbing a wireless signal over the air, right? Through jamming. Because wireless, there is broadcast and superposition properties of the wireless medium that makes it very easy to perturb data over the air. So in case, and that seems to be the case, deep learning starts to be implemented more and more in wireless, this adversarial issue will become a very critical issue to the success of deep learning in a wireless setting. In general, we think, so the literature of adversarial deep learning over the past 5 years has been going like this. Someone proposes a defense, and then someone comes and breaks this defense. And then someone comes and proposes a new defense against the new attack, and so on, right? We feel that this literature can make use of a little bit of organization. So some of the questions that we think are important is basically consider adaptive attacks that could change with time after it observes the defender behavior. And that brings you to, instead of designing a new defense or a new attack, is to come up with frameworks for defense strategies and attack strategies, right? As well as for the right metric, right? So let's say I come up with a new defense strategy. What's the right metric to judge it, right? So the robustness of the defense to changes in the attack strategy or to a smart attacker should be taken into account, not just measuring it against the attacks that exist in the literature so far. Capturing the value of knowledge, I think, is very important, because it makes you, so let's say I'm designing a system, right? There will be a cost to physically keeping things secret, but it's usually doable, right? So there is usually a cost to physical security, right? But we don't know, so it's important to identify what are the important parts of the system that should be protected physically, right? If I have limited resources to physically secure only small parts of the system. So capturing or understanding the value of knowledge of the defender and the attacker about each other's strategies, how much each piece of information buys them, that's important. Modularity is very important, because when I'm designing a system, I want it to be modular, right? So let's say I discover a new attack against my system. I want to be able to protect against the new attack by adding only a new a simple modification to my system, right? And lastly, the computational cost we think is important, because that's traditional computer security was based on basically designing functions that are hard to invert computationally, right? So the computational cost of circumventing a defense, that should be taken into account in judging a defense. We had what's called a vision paper in the Journal of Computer Society with many colleagues at Purdue, and I highly encourage you to check it out, because we talked about many of these aspects that I just discussed. Now, one certain line of work that I want to highlight is for detecting adversarial attacks through having deep learning modules that monitor the hidden layers, right? I think this paradigm is useful in general in capturing uncertainty, like how uncertain your deep neural network is about its output. And this paradigm of like having AI modules observing the original AI modules could be useful in many settings, not just adversarial deep learning, maybe also for self-driving cars, so that the car can tell you, like some modules are monitoring the inner workings of the car to tell you when the human driver should take on, because there is a new situation that we are encountering, okay? So let me, like in the next 15 minutes, let me discuss 5 minutes each, the 3 applications that I want to discuss. So the first one is applying deep learning for wireless. For these 3 reasons, I think it's a good idea to apply deep learning in wireless. The first one is that wireless is moving towards a new vision where you have a lot of heterogeneous networks. Heterogeneous means 2 things. Heterogeneous in technology, right? So a merge of different technologies that operate at different frequencies, maybe like satellite communication with millimeter wave, with low frequency communication, and so on. and at the same time heterogeneous in a sense that people are envisioning, and I think there is kind of a national interest in having heterogeneous, like independently designed networks that can coexist easily and quickly. And that was the vision behind the DARPA Spectrum Challenge that I'll say like 2 minutes about it. So in these cases, if the network is heterogeneous in technology and independently designed networks, then it's very hard to find a concrete model for the environment. At the same time, it's very easy to collect data because of the small time scale of wireless communication. So in minutes, you could collect thousands and hundreds of thousands of observations if you are processing received wireless signals. So these are the two main motivations whenever you use deep learning. And the third is that many of the operations that are applied in deep neural networks, like the convolution in deep neural networks, is not exactly mathematical convolution. It's what's called mathematical cross correlation, but it's very similar to the mathematical convolution that's used in matched filters, for example, which are used to process received wireless signals, right? So that operation is already existing in both applications, like in wireless, in processing received wireless signals, and that capability is available in the current state-of-the-art deep neural network. The other one is that many of the layers in state-of-the-art deep neural networks are basically about capturing temporal correlations through recurrent layers, or what's called long short-term memory layers. That's the most commonly known one. And capturing temporal correlations has a lot of utility. You could imagine it for processing a received wireless waveform, for example, to identify the modulation type, as well time of arrival. Many tasks involve capturing temporal correlations. So we envision, in order to do a research in something that is as new as this, we envision a hierarchical approach, where first you build source identification tasks. So I am in a wireless environment, I receive a signal, I want to identify the sources of transmission, who is transmitting, who is contributing to that signal. And then if you can do that reliably, then you can build on it, right? So, and then you can analyze behaviors, right? So maybe I can analyze the behaviors of the other wireless users using the spectrum, like how they occupy that channel, how they jump from one channel to another, how responsive they are to my requests if it's another network, how reliable the information that they provide me, right? Let's say I can do that reliably, then I can use it to build even more and develop intelligence at a level of classifying a scenario. So maybe I'm in a downtown of a city, I am in a mall, like I know the behavior of other networks, I can build traffic models and so on. So in general, what's called context understanding. So we are trying to hit basically that, like whatever feasible to us to do in terms of research along that hierarchy. So in terms of source identification, we started to do some research in toy research problems. One is on modulation classification, the other is on identifying the channel index in the 2.4 gigahertz ISM band. And we made some progress in this, like very impressive progress in finding neural network architectures for these two tasks. And so I'll try to skip because of time, but there are some research problems that I think are interesting. One is, after you get good architectures for a specific problem, you could do subsampling, and subsampling is a known area in wireless research because it's useful in many things, including hardware cost, right? That you sample the received signals, not necessarily every, let's say 2 milliseconds, but you can afford to wait 10 milliseconds, right? And maybe you can do this subsampling in an irregular way. So we think there is room to do research in what's called data-driven subsampling, which is similar, but if you are curious, please contact me. I don't have time to explain that analogy right now, to something in feature selection called wrapper-based feature selection, which is basically depending on simulating the performance of the candidate set of samples for every for your learning task, right? So it's a task-specific subsampling that is based on the data. That's why we call it data-driven subsampling. Now, the second toy problem that we tackled was you're in the ISM band. So there are 3 wireless technologies: Wi-Fi, Bluetooth, and Zigbee. And these technologies have different channel indices. And we want from the received signal to identify the channel index. And the reason why we discussed these two research problems is that because there are data sets available in the literature. So there is a benchmark that we can compare to. Okay, and I think one of the, again, I wouldn't be able to discuss the results, but one of the problems I think are useful to consider is how to design training algorithms that are fast and efficient using what you know, the domain expertise about the wireless. So for example, how to choose the SNR, like to selectively choose your training examples according to their SNR values, according to the band, right? And maybe subsampling, right? So you can think of band selection as subsampling in frequency domain, right? So what's the right band to consider? What's the right SNR value? What's the right sampling strategy to consider if you want to minimize your training, the size of your training set, such that you can train online, or you have faster training algorithms for your deep neural network, right? One of the interesting research topics here is the sensitivity to the test SNR estimate. So let's say I have a test SNR estimate. What if it's off by 2 dB or 1 dB? How sensitive my training strategy would be? And then we designed some training algorithms that are inspired by things that exist in the deep learning literature. Like there is something called boosting, which is to adaptively select training examples based on the feedback you got in the training process so far, the training error and validation error. And we did it based on the SNR values, and you're welcome to read the paper on it. So then let me skip a little bit. I'll say just 1 minute about the DARPA Spectrum Collaboration Challenge. So I was fortunate to lead the Purdue, Texas A&M, and Raytheon BBN team in that challenge. The idea is to have different teams. They can talk to each other, right? And these teams, they independently develop networks, right? What's called a collaborative intelligent radio network. And then the 10 nodes corresponding to each team is paired with 40 other nodes corresponding to 4 other teams in what's called a match. And this match depends on an emulator, right? So a combination of hardware and a simulation environment. That's called the Coliseum that DARPA built, and I think it moved to NSF right now. And the teams can only communicate with each other through a collaboration language, right? Through a protocol, a collaboration protocol. And basically it simulates multiple scenarios, and this was mainly driven by DARPA, like military scenarios. So the idea is basically what if we do NATO operations? Like in NATO operations, the different countries that are part of NATO, like they have different networks independently designed, and then in 1 week they want to coordinate in a shared spectrum quickly, right? And the incentives were both altruistic and selfish. So you have to deliver your own, satisfy your own quality of service requirements, as well as cooperate to facilitate the other networks to do the requirements. Now, just to summarize the other part, we collected a data set from a mature stage of the Spectrum Challenge, and then we are trying to do research using that data set, which is very interesting. It's relevant to, let's say, edge learning scenarios, for example, because we collect data at every node in our network. And we are trying to get insights about the different architectures that should be used and their implications on things that are custom to the wireless problem, like propagation delays, for example. Okay, so I think this is an excellent topic for research, and we are only at the start of it. Now, just 3 minutes about each of the other applications. So we recently had a patent on using machine learning for network intrusion detection, right? And the idea is basically to satisfy these properties that correspond to the acronym LiDAR, which is basically to have an architecture where there is a mechanism to introduce lifelong learning updates to the different machine learning modules. And you have intelligent, basically you combine different machine learning modules from unsupervised machine learning that has signature for attacks built in, and unsupervised anomaly detectors, right? And you want to combine also the feature extraction. Let's say I'm in a wireless network. I want to extract network level features at the IP level, as well as physical layer features. And I want to be agile and robust against changes in the environment, as well as an attacker that could be smart or intelligent and adapt to my behavior. Now, the architecture in a nutshell consists of pre-processing components, right? And like filtering the input data and feature extraction, and then the machine learning components, and then decision support components that not only take decisions, but they give feedback to the earlier components. Now, I will highlight two parts of the architecture in 1 minute exactly. One is the decision support component uses what we call the rule-based brain, and that receives not just recommendations from the machine learning components, but also uncertainty scores, how confident they are. And based on the final outcomes, it provides lifelong learning updates or updates to the machine learning components. And that's related to the modularity that I discussed before in designing basically any cybersecurity system. And the other one is a new design for a honeypot. And the honeypot is basically an algorithm that lures the attacker. It gives them requests that look like normal requests in hope of stirring attacker behavior that we are most uncertain about. So we use, or the idea is to use what's called curiosity-driven reinforcement learning, which is basically a reinforcement learning driven by internal objectives or an internal reward mechanism instead of an external reward mechanism driven by the environment. And here, basically, the reward mechanism is information. So we want to maximize the information gain from the expected response of the attacker to my request. And at the same time, my request has to satisfy a stealth constraint. The attacker has to see it as a normal request, okay? Now, we think this architecture opens the door for many research problems, especially for the case of wireless networks, where you can imagine this decision support component altering physical layer parameters in order for the machine learning components that are in the intrusion detection system, in order for them to work well. So maybe I get conflicting recommendations that I decide that I am operating at a dangerous SNR level. So I tell the physical layer, we have to change the SNR because this is a very insecure environment that we are operating in right now. Okay. So again, this is a new area of research and collaborations would be great. And since we are filing the patent, so we'll be able to share more details. Now, last but not least, so this is an effort that I'm again fortunate to lead the engineering team for it. It's a big team, not just engineering, because there's a lot of fundraising effort. It's an autonomous racing competition that's called the Indy Autonomous Challenge, and the plan is to compete with physical racing cars, realistic racing cars, Indy Lights car, on the Indianapolis Motor Speedway in October 21. And before that, we are doing a simulation race until May 21. Our team is called Black and Gold because these are the colors common between us and our collaborator, which is the United States Military Academy at West Point. Now, this problem is very interesting because it has a wide range of problems that come together in an integrated fashion. So it's not just a self-driving car, it's self-driving car at very high speed. So the information you get from the sensors, which are either cameras or LiDAR sensors, between each snapshot and the next, a lot has happened. Maybe 80 meters have happened, right? So you need to employ a filtering or a state estimation mechanism so that you can basically extrapolate or interpolate between the different sensor values. Also, dynamic path planning or designing what's called the SLAM, some localization, and so this is basically the navigation algorithm that are localization and mapping that are commonly used for robot planning, right? And what's interesting here is how to combine it with the advances that happened in machine learning and deep learning in particular. And of course, many of the vehicle dynamics bring very interesting aspects to the problem, and I'm learning a lot from the mechanical engineering collaborators about this. Like, for example, things about tire friction, about estimating the throttle of the car from only the RPM and the torque, so that you don't have to estimate the throttle directly, but maybe it's easier to estimate the RPM like a human driver would do, the desired RPM. So there are many interesting topics regarding this. What got me into this problem is that I was advising an undergraduate student club at Purdue called the Autonomous Motorsports Purdue. And we were basically developing a go-kart for what's called the EV Grand Prix, which is a competition that Purdue is organizing again, but in a small track, since these are go-karts of the Indy Motor Speedway. Now, I like this effort. I'm very excited about it also because I started a new class this semester with what's called vertically integrated project class, which is undergraduate class in all years from first year engineering until senior. And the class has 26 students, including 12 first year. And they are trying to carry out projects, right? So there are different student sub-teams, one navigation, one software, one electrical, and so on. And this year, we are offloading projects out of the experience that we have, like the graduate students, out of their experience in the Indy Autonomous Challenge. So we are actually building like tutorials out of the challenges that we get for the undergrads. And this is really cool because the undergrads are surprising us in all kinds of way in their impressive ability of doing tinkering and finding things that work in a very efficient way. So we had good news recently. There is something called hackathons. It's kind of scrimmages that DARPA Spectrum Challenge had something called scrimmages. Here it's hackathons before the simulation race. So every 2 months or so, there is a hackathon. There was one in September, and there was a simulation race on the fastest lab without head-to-head on the Indy Autonomous Challenge. And we had the second fastest among all competing teams. So the second fastest time, and we were tying with Crimson, which is University of Alabama, and actually we are first in the U.S. because number one is Polytechnic Milano. So that was encouraging. We still have a long way to go, but we are very excited about this effort. Now, just in 1 minute, that's the most important part. I'll introduce you to basically the heroes behind this work that I presented. So top left, that's Shakti Wadekar. He works in autonomous racing. He's a PhD student. And then Ahmed Mohammed, a PhD student working on deep learning for wireless. Jen Yi is a senior undergrad working on adversarial deep learning for wireless. Rehana Mahfouz just received her master's, now works at Qualcomm. She worked in adversarial deep learning. Shafin Jamil, PhD student, works in deep learning for wireless. And Tolunay Sefi just received his PhD. He worked on information theory of interference management and deep learning for wireless. Tingwei Huang, PhD student, works on information bottleneck. Anis Ahmed, PhD student, working on using deep learning for plant disease detection, agriculture. That's a problem I didn't talk about. Sharan Ramji was a senior undergrad. Now he's at Stanford, and he worked in graduate school at Stanford. He worked in deep learning for wireless. And Kirti Sivamani is a senior undergrad. He works in adversarial deep learning and just received an offer from NVIDIA, which is very exciting. Rohan Manna is a PhD student. He works on autonomous racing. And Shreya Ghosh is a master's student, and she works on machine learning for network security. Thank you. Sorry if I exceeded the time a little bit.
Ali, thanks. So maybe you can stop sharing screen, and then the discussants can. Who wants to go first? Armin, do you want to go first? Okay, yeah. Why don't? Yeah.
Let me share my screen. Okay, thank you, Ali, for your great talk. So I wanted to go over two of the subjects. Both of these concern the machine learning for wireless project that you mentioned. So the first one is basically efficient training of deep classifiers for wireless source identification using test SNR estimates. This is the title of the preliminary paper on this subject. So I'm just going to quickly go over the motivation and the results, and then some of my comments. So basically, the motivation for this work was to form an intelligent understanding of the spectrum. This is to identify different sources or types of transmissions. Like Ali mentioned, this is basically trained on two different data sets. One, the problem is to identify basically 1 out of 10 different modulation types. The other is identifying between different types of channels in the 2.4 gigahertz band. For both these problems, the data that we have is basically sample vectors of IQ samples for fixed durations. And by looking at this spectrum, you want to basically see if you can differentiate between these modulation types and channels. So in previous work, this has been addressed. The main addition in this work was to see whether how SNR estimates actually play a role in this sort of problem. So the models that are trained are a combination of convolutional neural networks and RNN networks. So both of these, I think the motivation is that since these are time signals, you want to be able to leverage temporal dependencies. Convolutional networks having an advantage in short-term dependencies, basically, and RNNs are good at capturing longer-term dependencies. So both are good candidates for this sort of data. And then what's compared is basically training using all the available data or choosing between different SNR values. So for you split your data into different subsets for different SNR levels, or use basically SNR values through a boosting algorithm, which is guided by cross-validation. And then for each test SNR, for each test sample, you go to the model for that specific SNR level for the test sample. So the main observation here is that when you train using these guided algorithms, you get better accuracy, especially for lower SNR values. So this is, so I think the intuition here is that the SNR level sort of changes the characteristics of the signal. So when you have data sets with mixed SNR estimates, that limits the generalization capability of your model. So it's better to have homogeneous data sets for this problem. And when you have estimates, the other takeaway is that it's better to train with optimistic estimates rather than estimates that are lower than the actual values. So I think one important factor here is that, well, when you have this sort of a boosting algorithm, it reduces the size of your training set, which can accelerate training. But what I was interested in is basically how can you leverage correlations between samples with dissimilar SNRs, basically. Is there a way to feed these SNR estimates into your network so that the network can adjust its prediction accordingly? So that you have basically a network that's equally good for both low SNR and high SNR signals. Yeah, so that's I think one big takeaway from this work, especially when you have smaller data sets. Yeah, so this is my comments on this work. Ali, if you have any comments, you can go ahead. Otherwise, I can go on to the next one.
Yeah, I think that's a very good point. And so the idea is basically these correlations are very hard to know other than in a data-driven way in if the environment is complex, because you don't know what's happening. Like maybe there is multi-path interference or something like that. So so the relevance between the different SNR between the data at different SNR values, we think that could change dynamically, and it's hard to find a global pattern. That's why we do it in a data-driven way. But the optimistic SNR estimate thing is something that we found to be consistent across SNR values and across tasks for the two different tasks that we consider. So that was interesting. Maybe there is a theoretical reason for it, but this is a purely empirical observation. That if you say you're not confident, your SNR is probably between -2 and 2, and you're not sure which one is it, then it's better to go with the 2, to choose the data set to train at 2.
Okay.
Yeah.
thank you. Yeah, so let me then go on to the second one, which is actually a very similar, they're connected, I think, and they both fit into the framework that you mentioned for deep learning driven wireless communication. So in this one, and the data set used in this one comes from the DARPA challenge. You basically want to know whether you can automate spectrum management for designing intelligent or smart radios that coexist with independence, basically without them directly coordinating with each other. And the first step here, I think, is, and as the paper mentions, is you want to know before sending a transmission whether it's going to result in an error, basically because others are transmitting on the same band, or maybe there's significant interference on that band. So what you have here is basically values that come from monitoring the spectrum itself, and your decision for your transmission, the modulation and coding scheme, the transmit power, the channel allocation. So then you combine all of these features and then you feed them into a deep learning model. And the target of the model is to then predict frame errors. Yeah, so previous work uses either simulated results or they do not necessarily monitor the spectrum. They just use the decision of the transmitter itself regarding its like modulation scheme. So this sort of uses a real world measurement and uses all these diverse set of features. So then the models that are compared are, like I said, so these are time signals again. You have these measurements for each of the frames that you have attempted to send previously. And you compare recurrent neural networks, convolutional neural networks, or fully connected ones. Again, the takeaway or the result of the paper is that LSTM models perform better, which is, I think, because of their power in capturing longer term dependencies, which is why they're also used very extensively for text analysis. And then there are different strategies are compared for basically constructing your training or test samples. One is you have measurements from different links or bands. You can either split based on links so that for every test sample, you haven't trained on any frames that you have attempted to send on the same link, which sort of makes it a harder problem because different links can have different characterizations. And then the other one is basically having
Armin, can you speed up a little bit? He has a 510.
Yeah, so
just leave. So, I mean, and I want the other speaker also, other discussant to also finish. So,
all right. So just so yeah, I guess the takeaway here is that how do you combine these two different schemes to build basically smart radios, which then becomes sort of a reinforcement learning problem. And how do you achieve like stable smart radios that can coexist with each other without necessarily directly coordinating? Yeah, so yeah, that's basically my take.
I can just give a quick comment on one thing you mentioned is the LSTM. So in actually like an improve, like as we revise that work, we have an explanation based on observations of this LSTM thing, like a possible explanation is basically when you so we use features at the transmitter before you transmit, right? But the frame error happens at the receiver. And in that time, there might be a propagation delay that made you not observe certain interference or something happening on the channel at the transmitter, but the receiver would observe it. Now, as you monitor a history, the history of these parameters, then if you use a recurrent neural network, it can extract semantics like that. And that can help improve the accuracy.
Okay, yeah, that makes sense. Yes, thank you. So please let me stop sharing then so the next discussant can.
Stop sharing and then allow Igdip to take over. Sorry.
Thank you.
All right, so I'll start with my slides then.
Yeah.
Right. Thank you for the talk, by the way. And I'll quickly go through this paper's summary and then just ask a question. So one of the papers that you talked about was non-intrusive detection of adversarial deep learning attacks we observe in networks. And well, the general intuition, a quick summary in this paper was that if you have an adversarial sample in comparison to the clean sample, well, adversarial perturbations are sort of imperceptible, but if you go to some deeper layers in the network, there actually turns out to be significant amount of noise, and based upon that noise, perhaps we could tell that the current sample is an adversarial sample, not a clean sample. And based upon this philosophy, based upon this motivation, the paper that you guys have proposed the solution that you have these early exit modules, these detector modules, which will basically take in the feature map and try to give a binary output which says whether the sample is noisy or not, whether it is an adversarial example or not. I suppose now my question here would be that the philosophy of exploiting noise, is that appropriate in the context of adversarial examples or not? And the reason behind this question would be that adversarial examples, there are certainly imperceptible perturbations at the input. However, a perturbation implies minimal change in distribution breaks the model. Basically, we are changing our model, our input slightly, and that's leading to misclassifications. However, rather than thinking of this in terms of noise at the feature level, shouldn't our philosophy be that that these noisy inputs, even to us humans, they are imperceptible noise, but we are still able to classify them correctly. So rather than discarding a sample, shouldn't we be thinking of how to yet match the distribution, of how to figure out a methodology which can adapt to this noise, rather than discarding a sample which was noisy?
Yeah, 100%. That's a good line of thinking. But let me clarify something. So the philosophy of monitoring the hidden layer is basically not just that you are monitoring something out of distribution, you are monitoring the inner working of the model. So in training, the model learns to extract certain features. Now, if the hidden layers are not working as they should, that means that the model is doing something it's not intended to do.
Mm-hmm.
So that's basically the idea. Not that yeah. So you're right. We should be able to generalize, but what we are detecting here is that the model is basically outputting something that could be random. So that's not what it's trained for. So you are right. Then after detection, there should come another step, which is how to update the model, be able to correctly classify a sample like that. Yeah.
Right. Yeah. So that's certainly something I've been thinking about. Yeah, that these are out of distribution data and how to manage that. So okay, thank you for that. And I guess I have a quick question on the information bottleneck stuff as well. So information bottleneck, as of yet, the way it's employed in deep learning, you usually use variational approximations to estimate the distribution, because actual estimation of the marginal distributions will be pretty complex. And the limitation to variational information bottleneck here would be that the variational bounds that people use, they're generally not accurate as if you increase the mutual information slightly. So there was this recent paper in ICML which actually showed that. So I'm curious to know what are your expectations on the practicality of information bottleneck in deep learning? Like, can we actually expect to use it for training our models, or will it generally be a framework, as for example this paper that you talked about, where they're observing phase transition? Will it be a method to probe deep learning, or will it be a method to actually train models?
So that's definitely a valid point that you mentioned, that the variational bounds to mutual information are often inaccurate. But I think it's worth, and I'm not doing that right now, but I think it's worth doing research into like how accurate is it with respect to properties of the distribution. Like basically what distributions are easy to use. Like
Yep.
we only know that the discrete case, and there are some results for Gaussian, which is not surprising in communication theory. It's also discrete Memels channel and Gaussian channels, which are known. But what needs to be known here is basically if I have an arbitrary distribution, how can I judge how useful IB would be to analyze to analyze this learning problem. Now, I think in general, and maybe I'm a little bit reiterating, I think it's useful in two ways to tell you whether the learning problem that is feasible with the model that you have or not. And the other one is basically to come up with regularization strategies that are inspired by the IB formulation. But that comment you have is definitely correct.
Okay. Yep. Thank you so much.
You're welcome.
So are there any other questions for Ali? If not, let's thank him. And as you mentioned, he's looking for people to collaborate with. So if anyone has any questions, please message him separately and he can, or sketch. I mean, I think the meeting notice might have also gone out. There's some openings to meet with him tomorrow as well. Yeah.
Thanks a lot for giving me the opportunity to present.
Yeah, so let me thank you. I don't, it's hard to do that in this context.
Yeah, you can clap on Zoom.
Yeah, I can. Well, I'm clapping.
No, there is a sign you can.
Yeah,
wave.
I know. Yeah, no, I know. But I was just joking. May as well do it in the right way as opposed to, so this is, you don't have to go everything virtual. Yeah. All right. Thanks a lot.
Thank you.
And, yeah. All right.
Have a good day.
Bye.